Howdy. Oh, that even worked here. That is so good. All right. Welcome back to the last set of talks for our inaugural annual event. Thank you for staying with us. And I have really deeply enjoyed the last couple of days. And so I will take the good 3 p.m. second day attendance to mean that many of you have as well. It is my pleasure to introduce Dr. Paul Balcombe, Senior Lecturer in Chemical Engineering and Renewable Energy from Queen Mary, University of London, also wins the prize for traveling the furthest distance to give a talk at an hour that to him feels after midnight. So thank you, Paul, and appreciate that you're willing to share with us. And please, go ahead.
Thank you very much. Can you guys hear me? Yeah. We're in. Super, thanks very much, guys. It's been a pleasure to attend for a start, and yeah, I'm glad that there are still some people around to hear us talk about something that's not frequently talked about in this environment, but also in most of the methane tour. So I'm going to talk to you a little bit about emissions from LNG shipping. So yeah, just to give you a tiny bit of a background. So I'm, as Erin said, I'm a senior lecturer at Queen Mary, and I've been working on methane for around about 9 years now, and it's evolved in a substantial way for me and for everybody else, as you know. And so LNG is one of my favorite topics, I would say. And the thing for me is that, whilst it's very clear that in the last decade we've made loads of progress in understanding methane across different sectors of the supply chain, the real crux is that for LNG, we've got so much more progress to make. It's really lagging behind other areas. And so there are so many gaps, not just in data availability, but in our understanding. And so in our understanding of what to do about it to make life a bit better. So the thing here is that there are nearly zero measurements of methane emissions from LNG ships. So we've done a reasonable job of the upstream, midstream side. There are a couple of measurements around the LNG liquefaction and regas and storage. But there's really hardly anything when we're talking about LNG transport, including the loading and the unloading and the actual transport phase. What I wanted to do here was do sort of a traffic light system, but I realized that there wasn't really any green areas of the LNG supply chain yet, but just thinking from a global perspective. So, and the really challenging thing from my side was that the assumption has always been for LNG systems is that we have very low emissions. And so when you sort of go in with that assumption of having very low emissions, it's difficult to garner support to go out and really sort of spend lots of money studying these things, right? But it's not until you actually go and study these things that you realize, oh, it's not quite so simple as this. It's a dangerous default. So at the same time, as we've heard, particularly yesterday, LNG is on the rise. So we're seeing way more transport and year-on-year growth on LNG. So it's becoming much more important to really understand what these emissions characteristics are, because if you do see some substantial emissions on the shipping side, it's going to ruin your credentials of the whole supply chain. So this is the topic of what we're talking about today. It's the transport side of things. In terms of what we currently know, the honest answer is not that much. So LNG shipping is a mixed bag, right? So we have currently got around about 670 ships in operation at the moment. So these are LNG carrier ships. They are quite variable across different technical characteristics. So I've just robbed somebody else's graph here. So this is the number of ships we've got, a different age range. So we've got quite a good distribution of age range, although perhaps fortunately there's a really large contingent of younger ships. Also, cubic meter capacity, so the size of ships are quite varied. And what we think is all important, the types of engines that are used in LNG ships is very different across the different ships. So we've got lots of different engine technologies that we know are going to emit different types of emission profiles. So what do we know? Not that much, but we know that there's a lot of variation in the technologies. There's a lot of variation in there's lots of different operators, and so we know that there's likely to be some variation here. So what we did a few years ago was to start off by thinking, well, what are the potential emission sources? And so just really roughly, we started looking at methane, thinking about what are the key emission sources. So the standard ones you'd think of in the other stages. So vents, fugitives, flares, maintenance, and also engine slip, which is kind of part of the incomplete combustion part. If we're going to look at published data, there is a little bit of data on engine slip emissions, so which is why we know that different engine technologies is a really important thing to think about. There's basically nothing on any of the other emission sources as well. So this is one thing that we really have to address. But for the data that we do have, so this is a copy from a publication that we did a couple of years ago. Engine slip data for different types of engines. So this is on the Y, we've got the methane emissions intensity, so the percentage of the throughput, and there's a couple of different, or 4 different engine categories. I don't need to really explain the specific acronyms. We don't need to go into the detail, but just to know that there are different engine categories. They have quite different emission profiles from what we know currently. So the circles are individual measurements. Actually, if we're honest, most of these are test engine measurements or lab tests, so that often they're not in situ, real life, in operation measurements, which is an issue. The next thing is to say that these last two, which are particularly the last one, the LPDF, that's low pressure dual fuel two-stroke. So this is a really popular engine for LNG carriers now. And up until very recently, there were basically no real life measurements of this engine in operation. So we thought the emissions would be about 2.5% slip. So 2.5% of what you put through the engine slips out. But we need to corroborate. So the other thing that we never really talk about is that these we talk about the main engines. But when we think about these big LNG carrier ships, you've got a couple of main engines, and you've got a set of auxiliary or generator engines as well, right, that are generating the electricity. That's typically how it works. And there's really nothing on these generator engines as well. And they produce a lot of power. So we've got a little bit of an issue with text there, so I can tell you if you can't read it. So this is a study that we did in 2021, and we published it in 2022. This is our first ship study. So the idea of this was to get on board a ship, conduct actual measurements of methane emissions across all of the different potential emission sources, do a full round trip, so trying to understand what the emissions profile might be whilst you're filling the vessel, whilst you're loading, whilst you're actually doing the cargo-laden transport, what happens when it unloads, and also the ballast return journey as well. So really trying to get a characterization of the whole round trip. Really this is a sort of a first of a kind, so we don't think that anybody had done a total emissions measurement campaign on an LNG ship before. And there is a good reason for that. It's because it's quite hard. It was a really tricky thing to do. It cost quite a lot of money, and logistically it was challenging. I think Fiji mentioned that we had a small issue at the start, which was, I think, I could probably blame myself for this. So we did this during the time around COVID, and I wasn't actually allowed to travel from the UK directly to the US to board the ship at the time. So I had to spend 2 weeks somewhere else. So I chose Cancun, which I'm sure you can sympathize. So I had to spend 2 weeks in Cancun, and which sounds terrible, but actually it wasn't ideal for 2 reasons. Firstly, I was desperate not to get COVID, and because obviously I have to test before getting into the US, and we'd overlapped with spring break. So anyway, it was a danger. And the second thing was, as soon as I'd carried lots of equipment with me to actually do the measurements, and when I got to Mexico, my equipment all got seized at customs. So this was one of my first big projects, and I was fairly distraught. So we had to do some serious rectification. So just like to do a shout out, thanks to Matt Harrison and Fiji and CAMS for helping to sort out lots of these issues. Anyway, So the idea was how do we actually measure effectively an LNG carrier ship, and what do we think the emissions are from this example, and how can we then look at further other examples? So the ship that we chose is actually this ship, so it's the Gaslog Galveston. So owned and operated by Gaslog, chartered by Cheniere. It's actually a fairly new ship at the time. So this is actually only its second voyage. So it was a new ship with very new technologies, which was an interesting start. It had one of these engine types that is a low pressure dual fuel two-stroke that we didn't really know anything about in terms of real operational data. So the first cargo was in January. We boarded it at the end of March, and we spent a month on the ship. So it was, I should say, there was 3 of us conducting the measurements on the ship. So it was myself from Queen Mary plus colleagues from SLR who did a great job, and we spent a month on the ship as a whole round trip. We tried to look at every different source of emission. So we looked at engine exhausts. So on this ship, there were 6 engines, so 2 main engines and 4 generators. And so we connected up what's called an FTIR system to do sort of some stack emissions monitoring on each of those. We looked at, so the GCU is basically the flare for the ship, so the gas combustion unit. We looked at vents, so there were actually 5 vents on the ship that we looked at, and we also did fugitive emission surveys as well. So we were walking around every day. We walked around, scouting around for fugitives. We probably didn't need to go every day, but whilst you're on the ship, there's not a lot else that you can do. So we did a lot of fugitive emission surveys. So that's how we did it. As well as collecting the methane emissions data, what we thought was going to be really important was to understand what was going on the ship at the same time. So we collected as much information as possible, not least having interviews and talking to the operators all the time, but collecting minutely data on the engine gas mode, the loads, the temperatures, the boil-off gas. So BOG is boil-off gas, which is fairly important when we're thinking about methane emissions. The diesel fuel consumption as well as lots of other stuff. So we collected loads of this data so that we could plug it into our models to really understand why we see the sort of the variations in emissions over time. So in terms of the results, I'll give you a really brief overview. I guess the numbers don't particularly matter. It's more the proportions that you might be interested in. So we did look at both CO2 and methane emissions. Forgot to mention that. The methane component was an important part. Okay, so we express the results here as grams of CO2 equivalent per ton, but we also look at just the methane emissions. And perhaps for this audience, what's maybe important here is that we estimated the methane emissions were about 0.1% of the LNG that was transported and delivered. Okay, so the methane intensity overall was about 0.1% of what was delivered. The other interesting stuff to talk about is where the emissions chiefly came from. We saw very, very little emissions associated with our vents and fugitives. Perhaps it was fairly clear we were going to not see a lot of fugitive emissions because it was quite a new ship, and this may vary across different ships. But what was perhaps most interesting to us was the contribution from the generator engines as well as the main engines. So the hashed stuff at the top is the methane emissions from the main and the generators. Bearing in mind, the generator engines were a lot smaller than the main. Let me just look if I've actually included the data here. No, I haven't. So they were a lot smaller in terms of their power than the main engines, but they contributed more emissions because they were much more slippy. So we looked a lot at the methane slip and how to characterize the methane slip across the different engines. So I mentioned that there were 6 engines here. So we've got M1, M2, the main engines, and G1 to 4, the generators. And the methane slip rates, so how much of the methane slipped through uncombusted compared to what you put in, varied quite substantially across the engines, right? Should say, main engine 1 or 2, identical. Generators 1 to 4, pretty much identical. I think actually 2 and 3 were the same, and 1 and 4 were the same. But we saw very different emission profiles when you look at the averages. So slip rates between 2% up to 16%. These are averages across the whole journey. So you actually saw quite a lot more variation within that. So it's not an inconsiderable amount. There we go. So I've written here. So the power rating of the main engines were about 11 megawatts and 3 to 4 megawatts for the generators. But the slip rates were much higher for the generators. So you normally only operate the generators two at any one time, right? So they're not all operating at the same time. There's redundancy there to make sure we've got sort of operational effectiveness. And I should say that typically it was generators 1 and 3 that were working most of the time. They had some issues with the other 2, which is why we saw raised slip rates for generators 2 and 4, so 12 and 16%. And so maybe the most important output from the study was really to look at how the engine slip rate changed over the engine load, so how much you're using the engine. So these two graphs, one of them, the left-hand side looks at the main engines. So each line is one of the engines. So the blue is 1 and the orangey one is number 2. And I've included some of the sort of the uncertainties around some of these measurements here as well. And so what's really clear here is that whilst we saw a relatively flat profile across the main engines, they weren't the same. And when you get to very low loads, you do see raised slip. With the generators, it was a bit of a minefield. So we typically saw between about 25 and 75% operation, and below 40% engine load for the generators, you saw really high emission rates. And so this was something that was quite surprising to us. It perhaps shouldn't have been that surprising, because afterwards, when we came back, we asked for the sort of the manufacturer's spec, the technical NOx profiles, and I should say that these engines actually performed as they were supposed to perform. They just hadn't been designed to minimize methane slip. So this was actually not outside the sort of the normal operation zone of the generator engines. They were just not designed for minimum methane slip, which was a little bit surprising to us. So, but the main thing here is that at low loads, you've got really high slip rates. And so it kind of gives us a fairly substantial opportunity. Before I talk about opportunity, also, can I just say, I'm about to play this video. It's got a really annoying volume to it. So if we could turn off the volume, that'd be great. Thanks. So just to say, so vents and fugitives, really, really low. We looked at all of the routine, well, there's basically no routine vents on the round trip that we saw. The only vents we saw were there's a couple of vents from maintenance, and then there was some venting associated with engine mode switching. So these are dual fuel engines, so they sometimes use diesel, and they most of the time use gas in this case. But they sometimes switch between the two. And when they switch between the two, they often vent out big slugs of methane. And this was one of the vents. Sorry, I've got really dodgy camera skills, so apologies for the bad one. But we saw some quite strong sort of slugs of gas coming out when it switched. The really interesting thing for us was that we didn't realize how much the engines were going to switch. So it switched 86 times during our voyage. And the reason they switched was, like most of the time, it was because there was some sort of an upset going on. They also switch when they're at very low loads as well. So that was a learning lesson. But overall, compared to the engine slip, it didn't really register. And across all of the fugitive surveys that we did, we only found 2 fugitive leaks. So bearing in mind that I was looking at fugitive emissions pretty much every day, we have found 2 relatively small leaks across the plant. So it was a bit of a joyless activity, I have to say. And so, yes, so generally really low venting and fugitive emissions. That may not be the case across all ships, particularly older ships, different operators, but this is what we found for this one. So the key question is how we can reduce emissions from what we've learned, and the most obvious opportunity is thinking about if we can change our engine load profiles to reduce slip. So I've just put another graph which looks at what the total greenhouse gas emissions might be with the GWP 100 at different engine loads. And so the gray bit is the methane contribution. and the red bit is the CO2. And so normally we were operating the engines around about 40, 50%. So you can see the methane contribution is around about half there. But if we increase that to 80%, you're nearly halving your greenhouse gas profile. And so there's a potential opportunity to there, for example, to be operating only one engine at a much higher load, or changing your operational dynamics. Obviously, there are limits to the feasibility. It depends on what the other operational constraints are, right? So there are safety issues, there are technical issues and operational feasibilities and standard operation procedures. But that's why we really need to talk to the operators to understand what we can do and how we can drive things down. So, yeah, at 80% load, methane slips about half from what we were normally working on. So we think this is a really good potential to reduce. So just a couple of conclusions from this, and I really want to talk about next steps, so I'll be super quick here. So yeah, CO2 emissions, I didn't really talk about this at this point, but CO2 emissions were quite a lot lower than what we normally assume of LNG ships, but methane was a little bit higher. So our total average engine slip rate across all the engines was about 3.8%, so it's quite high. What do we need to do next? So this is one ship out of 670. We need to look at more ships. We need to cover more ground. But we also really need industry self-monitoring, right? So there is nothing stopping everyone from, except money, from continuously monitoring engine emissions. We have the technology, we have the commercial available technology to do that. And this does need to happen. It is happening in various ships. We've talked to Cheniere lots of times, and many of the chartered ships do include SEM systems. We need to understand how much is monitored. There's not really a record of how much is monitored, and how good are these monitoring systems to really judge what information we can glean from it. But we need to do a bit more research, of course, so we need to get a more representative sample of ship measurements. We need to understand what is monitored and how it's monitored, understand the sort of the precision and what we can get out of it, and get a better understanding of what these emissions are and what the levers are that we can pull to drive these down. What I think we also need, and this speaks to the MDL stuff, is a tool for better estimation of ship emissions. And we can only make that tool if we've got some more better data to do that. So I shall leave it there. Thank you very much.
Okay, thanks, Paul. So comment and a question. First comment is we need a better tool. There's a poster out in the back from Kirsten Roselot, who's in the audience, describing basic formulation of a tool. And one of the, as you construct a tool, one of the things that becomes clear is that these generators, which have such high slip, are operated preferentially in certain parts of the voyage. Thinking about when the ship is underway, it's mainly the main engines, but once you're maneuvering and undergoing other parts of the ship's activities, you wind up with different loads on the generators versus the main engine. So would you like to speak to that a little bit?
Yeah, absolutely. So the operational profile of all the engines changes depending on where you are in your round trip. So when you're loading and unloading, there's much more of a duty on the generators. That might work quite advantageously if you're thinking that engine load increases results in reduced slip. So if you're using them like harder, then you'll reduce your slip. So actually that's quite a good one. I think the issue is that you've always got some generator requirement. So the, what do you call it, the hotel load and all of the sort of the energy requirements from the process. You've always got some requirement on the generators. I think we saw as you could see in the graph, you saw a much flatter profile on the main engine. So we see less of an impact when you're sped up or slowed down. But yeah, I think the focus really needs to be on better understanding the generators.
All right, let's thank Paul again.
Thank you.